Okay, so my topic today is about deterministic Ethernet for scalable modular avionics. So to my agenda, I first want to present you what is the state of the art. And I'm here really focusing on deterministic, fault-tolerant voting computers. And then I'll talk a little bit about synchronous deterministic Ethernet. Then it goes a little bit into the scalability of these architectures. Then what space components are currently available and what are we currently working, and I follow that up with a conclusion. As you may know, so in a lot of the spacecrafts, currently you have a voting architecture, which is typically using the let's say very deterministic protocol MIL1553. So in this architectures you typically have a 2 out of 3 or a 3 out of 4 voting system. So you have multiple flight control computers. Everyone is connected to a MIL1553 bus lane. All the bus lanes are deterministic. And now what you do is you have on the bus multiple components which are redundant on all the bus lines or on some of the bus lines. And the big challenge there is to vote between the different data which you get from the different components on the bus. And to align the state within all the flight control computers, so that you vote with the same state in all the computers. And the question is, how do you do that? So typically you connect these flight control computers via a point-to-point line, and with this point-to-point line you typically add a synchronization between them. And you add a high-speed data communication, because in case of one of the flight control computers, so if one of these computers fails, then if it needs to recover, then you need to copy the state information from one to the other, and therefore you need to have an additional communication, because typically the MIL1553 bus is not capable of that because of performance, and you do not want to keep the fault containment in one bus line and do not want to copy it over. In case of a fault, typically you disconnect a bus line or from the bus controller. So the bus controller always tells the bus what is going on the bus, and if there is a fault, the majority disconnects the one which is faulty from the bus. So this is a good approach, but there are some disadvantages. So what you need to support in this approach, you need to support multiple protocols. So one for the deterministic communication, which is the MIL1553 bus in the example which I showed before, which is from the performance quite bad, so it goes up to a maximum 1 megabit. What you need in addition is a synchronization protocol or a synchronization between these computers to be able to vote on the same state, that you know that the point in time when you can vote between them, and you need a high-speed communication. So for this architecture you need to support 3 different protocols, which brings you to additional wiring. So there is a lot of wiring involved, and you need a lot of software that takes care about the synchronization, the redundancy management, the fault masking, state exchange, reintegration, and so on. And this is quite a very heavy complexity which you add to the system because of all these functions you need to support, which can be taken over by an intelligent protocol. In addition to that, you have a lot of testing efforts because you need to test all these protocols, and it's quite tricky when you perform physical separation and reintegration with a bus like the MIL1553 bus. So now we are looking to what other solutions are available, and here it shows you the big picture of what we call time-triggered Ethernet. So this time-triggered Ethernet consists of 3 different traffic classes. So one is standard Ethernet, as everybody knows it. So standard Ethernet, best effort communication, but with no or very low performance guarantees. So you can add their priorities and so on, but it's quite low performance guarantees. In addition, there is the AFTX or ARINC 664 Part 7, which is a rate constrained protocol, which provides you some determinism because of a restriction of the bandwidth which is usable for a dedicated message or communication flow. And in addition, there is the SAE AS6802, which is a full synchronous communication protocol. This means there is a synchronization between the different nodes, and based on this synchronization, the traffic is scheduled, so it's hard configured on the line, and therefore you get a full determinism. So if you look now at one of the Ethernet lines, they are all coexisting on the same physical media. So you have the time-triggered packages, which are periodic and deterministic, which are predefined in the configuration table. You have this rate-constrained traffic, or the AFDX traffic, which is event-triggered, but has some performance guarantees. And you have standard Ethernet traffic in the gaps between the other traffic, which can be used and is quite flexible from the usage itself. Good, and now I want to talk about the synchronous traffic. So how does the synchronous traffic works? So first of all, you select some nodes which provide their clock information actively into the network. So for example here, these three nodes, they will now transmit their time information into the network to the switches. The switches will calculate a fault-tolerant average, and this fault-tolerant average, as you see it here, is then distributed into the whole network. So all the nodes get this time information, depending on the routing of the switch, and then establish a global time base. Yeah? And this global time base is now fault tolerant. So if I have a fault of one of the nodes, yeah, even if the node starts babbling wrong times, the protocol is able to handle these faulty nodes because of this average calculation in the switch. So the switch votes away the faulty nodes in the network. So depending on the fault scenario, this clock synchronization can be single or dual fault tolerance. So you can or is able to tolerate different faults. And this protocol, or with this synchronization protocol, what is performed is that every node in the network sees the same time. So this means after the establishment of the clock synchronization, there is no problem about the sending order of the packages, because every node knows exactly the time when a message is transmitted or when it is received. So with this time-triggered traffic, you always get the right sending order. And the protocol is fault tolerant, so you get one global synchronization, which is highly reliable. So let's now look so we have established a synchronization on a line. Let's now look how a packet is transmitted. So you have packet M here transmitted at 1045 from one node in the network to a switch. The packet goes to the switch on a dedicated port, and what the switch does, it enforces the arrival time. So it opens a window and checks if the packet arrives within that window. If the packet doesn't arrive within that window, the switch assumes that this node is faulty and throws the packages away. This means it leads to a fault containment region, because this node can never transmit babbling packages or wrong packages into the network. The switch then makes a store and forward, so it checks the packages, being Ethernet layout, CSC, and so on. And then after a defined latency, transmits it on a dedicated port to the next one. At the next switch is the same, so it's opening a window, it's checking the package, and then forwarding it to the receiver. And if there is now a receiver which is not aware of the time, for example, if you connect a standard Ethernet node into the same network, it can read the packet, but it's not aware of the global notion of time. But what you can see now here is what you get in this network is you get a defined end-to-end latency. So you exactly know when the packet is transmitted and when it is received. So you have full deterministic behavior of your communication based on this fault-tolerant global time or synchronized time. And here the precision or the jitter of the message depends on the clock synchronization. So the better the clock synchronization, the better is your determinism. Typically in the networks you got down below 100 nanoseconds. Good. So let's go on. So how does the fault containment of the messages itself look like? So we are defining here switches and end systems as two kind of fault containment regions. Yeah? So if there is a loss of a packet, it's always mapped to the respective sender, so to the last sender of the packet. And depending on the reliability targets, the switches can be standard integrity or high integrity. So if an end system sends a packet to the switch in such a network, you have to assume that if here the node is faulty and transmits a packet to the switch and that switch, and the switches are checking the windows, so they are able to keep the fault within this fault containment region. So the fault does not propagate over a switch. However, if one switch is faulty, then this switch would maybe start bubbling, so sending wrong packets, and then it would not be able, so for example, this end system here would not be able to differentiate between a wrong value from here and a right value from here, because it only has two packets, and it is not able to vote between them. So how can this be achieved, that with such a network you can achieve single fault tolerance? You need to have high integrity nodes. High integrity means that you have a node that in case of a fault fails silent, which means it doesn't produce an output anymore. And this can be achieved by a so-called self-checking pair. At CPU level, it's quite famous. It's called dual core lockstep, for example. And here you provide the same input to two independent blocks, which is a commander and a monitor. They are performing the same functions, and the output is compared. And if there is a different output from the commander and the monitor, then the output is shut down. And this ensures that there is a fail silence. So if we go back to this here, so for example, if this switch would be faulty, it would not produce an output anymore. This switch would forward the right output from the end system, and the receiver would see on one line no input, and on the other line the correct input. So how does this look like when we go back to the architecture before? So if we have such an architecture, we are now in a star architecture. So we need to define these synchronization masters. So these are the ones which provide their clock into the network. Then we need to define the compression masters. These are the ones who are calculating the synchronization. And as long as we have that, we can perform a single fault tolerant clock synchronization in the overall system. And for the data, since the FCCs are synchronized via the network, so which has been achieved with the synchronization protocol, they can now exchange, so they receive the same data from the senders. So for example, if this sender here and this sender here sends the same data, it goes to all the nodes. They are aware of the time information. And now they also have a high-speed link where they can communicate, so they can exchange the data in case of a fault. So this means in such an architecture, we can build up systems which can also do, for example, a 2 out of 3 voting. And the only protocol we need now here is a single protocol which allows the deterministic data communication, the synchronization, and the high-speed data exchange in case of a fault. The voting, so if these 3 flight control computers, they calculate a result, and this result is then transmitted to the receiver. The receiver now receives 3 times the same information and can easily vote between the 3 different instances of the message, of these messages from the different flight control computers. So what do we need for that? to support the protocol. So the switches and end systems, so the digital part of the switches and the end systems. Then the software drivers, firmware, and so on running on that or on the computers. A physical layer, so Ethernet physical layer, which need to be radiation hardened, for example. Cables and connectors, configuration tools, and development equipment. And I will now pick these two components, which I will show you now. So in the past 3 years, we were working on bringing out dedicated high reliable components for the switch and the end system controller. So this is the digital part of the network protocol. And these are in a ceramic 256 pin package and a plastic 400 pin BGA package. So the idea was to have a space component and a high reliable component. So they have the same radiation performance, but it's two different price tags. So for example, this is used by a launcher application, for example, in the RN6 launcher, which has a very, very tight cost target. How does this chip look like? So this chip has multiple blocks, and this is just a rough block diagram. So it contains the switch, the commander, and the monitor. So it has a self-checking pair included, which ensures the fault tolerance in case of a fault. So the switch port, so if there is a communication, the switch port shuts down and makes this fail-silent behavior to be able to achieve with two-channel a single fault-tolerant architecture. It includes this end system controller, and it includes also a CPU, which is responsible for the switch management. So when we now look a little bit into the different blocks, so the CPU is there for TFTP and SNMP. So TFTP for configuration loading onto the switch, so to define the routes of the messages. And the SNMP is there for standard diagnostics. I think you know that from standard Cisco switches, for example. There you also have TFTP and SNMP protocols. The end system controller here, so this is an end system with different host interfaces like PCI, SPI, or SpaceWire interface. So here you can run up to 3 ports, 1 gigabit full line rate on the PCI interface. Or you can use SPI, quad SPI up to 200 megabit. Or a SpaceWire interface to connect to the end system. The switch here, I have not put it on an additional slide, has 6 gigabit ports plus 19 100 megabit ports. So the switch engine here is capable of 16 gigabit ports throughput, and the whole design, if the whole design is running on the chip, it consumes a power consumption of 1.5 watts running with 16 gigabit full data speed. So the manufacturing is done on a 65 nanometer radiation hardened CMOS technology. And we have an internal shared memory, which is 1 megabyte, which can be shared between the end system, the CPU, and the switch. The CPU itself is a Leon 2 running on 125 megahertz. To the end system controller itself, so what you get is you get a NIC, so an Ethernet NIC, with a full IP UDP ARINC 653 layer in hardware. So for critical traffic, so for time-triggered and rate-constrained traffic, you can decide if you want to interface on a layer 2, or if you want to interface on UDP or on ARINC 653. So we have heard that before from the FACE consortium and so on. So ARINC 653, so this allows you to communicate on sampling and queuing ports. So you define your sampling and queuing ports, and the whole network stack, so the packing and unpacking of the data up to the ARINC 653 layer is performed in hardware. So you don't need to care in your software about implementing this communication layer. So this is a full picture of the chip. Yeah, it provides much more functionality. So it has 2 UARTs which support RS-232, 422, 485. It has up to 60 GPIOs. And then there is a watchdog timer. There are 2 interrupt controller, one for internal, one for external. It has 2 hardware timers. It has multiple of these SPI, quad SPI interfaces. So it's quite a performance system on a chip. And we tweaked the Leon 2 FT to run up to 125 megahertz, which is quite performant for a Leon 2. Another component you need when you want to use Ethernet in space is a physical layer, and we are currently working on a 10-100 megabit full radiation hardened physical layer, the first prototypes will be available in Q2 2017, and the QML product in Q4 2017, and it's quite a simple but highly robust 10-100 megabit physical layer. And there are other activities for a 10-100-1000 physical layer, which is, for example, TI will also come up with such a chip. Good, so for my conclusion, I want to summarize a little bit. So the network is capable of high deterministic avionics, so it's capable of a full determinism with fault tolerance. It can also be used for payload data. So the speed is quite good. It goes up to 1 gigabit, and the component can fully support that. So it provides this built-in fault tolerance based on the global time base. So you have a global fault-tolerant synchronous time, and it has integrated redundancy management. So the full redundancy management is handled by the protocol. The only thing what you need to care is about the application data and the application voting. Yeah, so it provides a very robust physical layer. So the Ethernet physical layer is extremely robust and has a very good bit error rate. And if you don't need the Ethernet physical layer, you can run it via LVDS, for example, on the serial, so for example, SGMI, like it is performed in the NASA Orion program. And it allows you to seamlessly integrate with Ethernet. So it's Ethernet protocol, and you can use standard laptops to connect to and debug and so on. Okay, thank you very much. If there are questions, I'm happy to answer.
Yes, hold on, wait.
Oh, sorry.
This is,
So it wasn't quite clear to me who's doing the redundancy management. Is it in the switch, or are the processors still doing the voting?
So you have to think that. So the network can only vote or take an approach of voting on the network level. Yeah? So, for example, what the network does is, if you send a message here, yeah, the voting is, or the first valid or whatever check is performed on the network level here by the end system. Yeah? But the application data, the network doesn't know about the application data. So the application data needs to be voted by the application itself.
other questions? Yes.
What sort of tooling is available to generate the scheduling topography across a large network?
So we have a full tool set for the, so where you define your high-level requirements of the whole network, and then it creates the tables for the different components. And there you have some mechanism which you can enable to be dynamically. So for example, for standard Ethernet, there are standard Ethernet features like dynamic routing in the switch and so on, or VLANs, VLAN tagging, and this kind of things. So in the switch per default, which are dynamically, or you can configure it also manually or statically, which is done by the tooling.
Okay.
And there you can decide if you want to configure the network level or the device level, or yeah. And we are extending now the tool via, let's say, the tasks of the operating system. Yeah, because you have to think when you use, for example, a virtualization, yeah, a hypervisor, then you could synchronize the partitions of the partitioned operating system to the network, and you could do that on multiple nodes, and then you can run different tasks in every partition, and then it's getting quite complex because you need to align the schedule of the operating system with the schedule of the network. Thank you.
Other questions? Very good. Thank you.
Thank you.